I think it's not high enough. Well, the point is they'll have the slides. The point is to see what it's like.
Oh, okay.
Well, do you want to down the projector?
So hi everyone. Thanks for coming to the 701 recitation. So we're going to do a brief review of probabilities and statistics. Okay, so my name is Ina and I'm one of your TAs. So if you have questions about what was taught in the last couple of lectures, please feel free to ask. So we're going to start with an introduction to probability theory, and then I'm going to talk to you about random variables. I'll discuss the properties of some distributions you're going to be using throughout the semester. I'll explain to you what an estimator is, and then I'll review a Barnabas taught in class about conditional probabilities and data. Okay. So first of all, yeah. Yeah, I don't have a loudspeaker. Maybe if you move like further down, you'll be able to hear better. So I don't have a microphone. I'll try to speak louder. Okay. So you were taught kind of the concept of sample space as the set of all possible outcomes of an experiment. Then an event in that sample space is a subset of it. The events that do occur, the outcomes that do occur. So a probability measure maps omega, the sample space, to the unit interval, to the 0, 1 interval. And it basically specifies how likely is any event in that sample space to occur. Barnabas reviewed the Kolmogorov axioms, which says that the probability of every event is at least 0. And the probability of omega is 1. Also, a probability measure is additive, which is the last line. So you were kind of shown how to reason with events in terms of Venn diagrams. So the probability of an event A is kind of the volume of the representation of that event over the volume of the entire space. You are not very likely given the formula for the event union and the intersection. So this is very easy to see using Venn diagrams. The probability of the union of the event is the sum of the probabilities of the events minus the probability of the intersection. Are those kind of is this kind of reasoning familiar to you? I'm not sure about the background, but okay. So okay, you should kind of know the properties of event union and intersection. That they're commutative, associative, and intersections just is distributive with respect to the union. Okay, how many of you have heard of the Morgan's laws so far? Okay, so pretty much everyone. Basically, these laws are easy to verify using Venn diagrams, but the way you prove things is by double containment. So an equality is usually, a set equality is proved by double containment. So remember that if you ever have it in the homework or the exam. Now, disjoint or mutually exclusive events are events for which the intersection is 0. Of course, the probability of the union of these events is the sum of the probabilities of individual events. For example, in a complement represents a partition of omega. And we'll talk a bit more about partitions later on. So a partition is a set of events that basically divide the sample space, covering it completely and being mutually disjoint. Be careful that this is not the same as independent events, such as successive and non-influential coin flips. So samples that are IID are in general independent events. So as I said, partitions are events that cover the entire sample space, and there are pairwise disjoint. The first, so the event reconstruction is writing the probability of an event using the probability of that event intersected with each of the events in the partition. Another useful inequality is Bayes inequality, which is kind of logical if you look at a Venn diagram. Okay, and then you were also taught Bayes rule, which we'll be talking about more later. So let's talk about random variables. So a random variable is something that associates a value to the outcome of a randomized experiment. So the sample space X represents the possible values of the random variable. So let's see how we translate an event to a random variable. So let's say, say we'll draw two numbers between 1 and 4, and let the random variable X be their sum. So I enumerated all the possibilities, all the possible occurrences of the event. And X of E represents the random variable X, the value of the random variable for each event. The table below summarizes the induced probability function of X. So for each value that X can possibly take, how likely is it that X will actually take that value? Okay, so clearly a value, when you draw two numbers from between 1 and 4, the most likely sum you're going to get is 5. And that probability distribution reflects this. Okay. So a cumulative distribution function basically is what determines the probability distribution of a random variable. So it's defined as the probability that the random variable will take less or equal values than the argument of the CDF, which is what's stated in the first line. So there are some properties to verify that a function f is a valid CDF. First of all, its limit to minus infinity has to be 0, and the limit to infinity has to be 1. So a CDF will always take values between 0 and 1, which is different than what will happen with a probability mass function. Now, it needs to be a non-decreasing function of f. Clearly, as x increases, the probability that the random variable will take values that are less than it will also increase, or at least stay constant. One other thing that I think Barnabash might have mentioned in class is that it has to be right continuous. In your homework, you'll have a set of functions for which you'll need to verify that they are CDFs. So remember these things. Now, let's talk about identically distributed random variables. So two random variables are identically distributed. If and only if, for all sets of values, the probability that the random variables will take these values is equal. Okay, so does that mean that the variables are equal? Well, no, it doesn't really mean that the values are equal. So for instance, let's toss a coin 3 times and let two variables, SH and XH and XF, represent the number of heads or tails respectively. Clearly, if I flip a coin, I'm not going to, and I sum the number of heads that I get after 10 flips and the number of tails that I get after 10 flips, I'm not going to get the same number unless they're like 5 and 5, but usually it's going to be something else. So the variables are not equal by any means. However, they do have the same distribution. I mean, it's equally likely that you'll get a head as that you'll get a tail, so it's going to be a Bernoulli either way. It's just that the variables themselves aren't equal. Now, you were also told that some of the variables are discrete and some are continuous. So they are determined thus by their CDF. So discrete variables have step CDFs, and continuous ones have continuous CDFs. So also the space of possible values that x can take is either discrete or continuous, depending on the variable. So for discrete variables, we'll talk about probability mass. Okay, so at every value that the point can take, you're going to assign a number, and that represents the probability that x is that number. Okay. Now, the probability density applies to continuous random variables, and well, that's the probability density for the Gaussian. But it's clear for both PMFs and PDFs that they have to integrate or sum to 1 over the sample space. Now, the way you compute, it's sometimes useful to compute interval probabilities, and the way you do it is you integrate the area under the curve for a continuous distribution. So this also leads to the explanation why for every discrete point in the continuous sample space, the probability is actually equal to 0. So if we apply the formula as it is then, we're going to end up with a right limit, which is actually 0 for that function. So imagine that area will become less and less until it will become 0. It will converge to 0. Okay. Now I'm going to introduce the notion of expectations and moments. So the expected value of a function g, depending on a random variable x, is defined as the integral of g of x over the probability measure of x. And the nth moment, I think there's actually a typo in the slide, so there shouldn't be in that top formula, there shouldn't be an e, it should just be integral of g of x, p of x, dx. Okay. So the nth moment of a probability distribution is actually the expected value of x to the n. A specific case of the nth moment is the first moment, which you were shown that is the mean of the distribution, and it's something you're probably going to compute very frequently or estimate very frequently. Now, the nth central moment is obtained by subtracting the mean and then raising to the nth power the variable, and you integrate that. Now, a special case of a central moment is the variance, which also you're going to be using and estimating in the coming months. Okay, now, all right, some questions so far, guys? Is this, so please let me know if this is like boring to you or if there's something you don't understand. So I don't really have a feel of what your background is. So if you feel like you're bored, just tell me to move forward, okay? So for multivariate distributions, these apply when we have more than one value that characterize an event. So let's uniformly draw two numbers. So we'll draw two numbers simultaneously from the set 1, 2, 3. And we're going to compute their sum and the absolute value of their difference. And this will give us, so let's say the two numbers are x and y. They're, of course, random variables. And we're going to compute x plus y and modulo of x minus y. So let's look at how likely each of the combinations are. So clearly, the sum will take values between 2 and 6, and the absolute value of the difference will be between will be 0, 1, or 2. And I enumerated all the possible combinations and how likely each occurrence is. There are of course 9 ways in which we can draw numbers, the 2 numbers between 1 and 3, and for each of them, I looked at the sum and the absolute value of the difference, and I saw how likely they are. So in red and in blue, you have what is called the marginals of the multivariate distribution. So we've got 2 values that kind of coexist, and each of the combinations has a certain likelihood. If we sum over, if we take that function, we call that f. If we take that function and sum over one of the 2 variables, we're going to get the marginal for the other variable. Okay, is that clear? Okay, so basically, if we sum over all the rows, we're going to get the probability distribution of the absolute value of the difference. If we sum over the columns, we're going to get the probability distribution of the sum. So for independent random variables, the joint distribution is the product of the marginals. Okay, so yes?
What's f?
F is the joint distribution.
Oh,
so it's a function of x and y that has to integrate to 1 over all combinations of x and y.
Okay, it's a probability distribution.
Yes,
okay.
it's a probability distribution for both of those. So, question for everyone: can you tell me if the 2 variables w and v are independent or not?
No.
Okay, so are they independent? Who thinks they're independent? Okay, who thinks they're not independent? Okay, right. So they're not independent because you can't really write that as the product of the marginal. Okay. So, so let's see some properties of common distributions that you're going to be using. So you were already taught what a Bernoulli variable is. So you draw a bit, and the probability with which the bit is 1 is p, and the bit can also be 0 with probability 1 minus p. So the mean and variance for this variable are very easy to compute. So the mean is p and the variance is p times 1 minus p. So we basically used the formula of expectation to integrate the function over the probability measure. So one thing, so the MLE is the sample mean. Has Barnabas taught you how to compute the MLE of Bernoulli, or do you guys remember? Okay, you did have a binomial though. So Bernoulli is just a very simple binomial. Okay. It's a binomial for which n is 1. So connections to other distributions, as I said, a sum of Bernoullis will give you a binomial, and the number of Bernoulli trials required for a success will give you the geometric distribution. Okay. Now, the binomial, you've discussed this in class, so I'll just state that the mean and the variance are NP and NP times 1 minus NP, and to get to these points, you require some combinatorics. So I'm not actually gonna. I was planning to do it on the whiteboard, but I don't think we'll, since it's already almost 5:30. I don't think we'll have time to do that. But one useful formula that you need is that you could use for the variance is that it's the second moment minus the first moment squared. That's sometimes useful in computing the variance. Okay. Now, the sum of binomials is binomial, and if you condition, you've learned conditionals in class. So if you condition on a binomial with another binomial, you also get a binomial. Now, some properties of the normal distributions. So when you sum two normals, you'll get two standard normals. You'll get a normal with mean zero and variance 2. When you the division of two standard normals results in a Cauchy, which is also something Barnabas mentioned. When you've got two normals that are independent but are not of mean zero, or they're not standard, the sum is still a normal. Yes?
I know this was mentioned earlier, but what exactly is normal means?
The normal is, so basically the function is, so for a standard normal, can you see from there to here? I don't know what you can. Okay. So something next is let's just say standard normal, right? Exponential so you're going to have this. So it'll be, so it's a variable that has this distribution. The reason why, yeah.
I just want to make sure for the first one, it also have to be x1 and x2 have to be independent with each other.
In the first one, they don't have to be.
They don't have to.
No. So the first one holds regardless of independence.
But the last statement.
In the last one, they'll have to be independent.
Okay. So it's independent, not disjoint. Not they have to be.
No. We're not talking about disjointness anymore.
So okay.
That's for the events. We're done with that. So we're going to talk about independent credit variables. Okay. So right. So that's how you operate with normally distributed variables. These are some things that you'll use later on. Now, if you have so let's look at a bivariate normal. So instead of having a single value, you'll have two values. But the two variables are correlated. So in that, so that matrix is the covariance matrix. And what happens with the covariance matrix is that when you have independent, the covariance matrix looks like this. So it's going to have stuff on the diagonal, and then everything else is going to be zero. Okay? Yeah.
What's the covariance matrix?
The covariance matrix. Oh. Okay, so the covariance between two variables signifies how related they are to each other, like how one of them can predict the other. So, well, I guess Barnabas didn't tell you this. It's basically how related the variables are.
Is it like defined in a specific way, or?
Yeah. So you'll have. Okay. So I guess you guys haven't taken. Okay, how many of you have taken a statistics class before? Okay, so no. Yeah. So you have. going to be okay. So you're gonna like translate this such that it's okay. It's kind of hard to give an intuition for this, but basically this is how it's defined. So it's kind of like for variable centered at 0, it's going to be something like this. So variables with mean 0 is this. And the expected value of the product of the variable. Okay? So the way you compute covariance matrix, let's say you have a normal. So x1 to xn is normal. Okay, with mean, say 0 and covariance will be sigma. Then sigma will be sigma ij will be the covariance between xi and xj. Okay, so does that explain your question about covariance matrix and how it's computed? Okay, so now everyone should kind of know what a covariance matrix is. Now, if the variables are independent, the covariance matrix will only have ones on the diagonal because clearly every variable is codependent with itself. So it's going to be 0 except for on the first diagonal. Okay? Actually, the way dependent variables are defined is that their covariance is 0. Okay, and also their correlation. Okay. Now, so given that you've got such a normal distribution with the covariance matrix that I wrote there, you can still sum them and get a mean, but the variance will be what I wrote there. So you'll have to also add the covariance. So it'll be the variance of each of the two variables plus the covariance between, plus 2 times the covariance between them. Okay. Okay, so far, any questions? Okay, well, we can continue with estimators. So let's say we have a sample from a distribution parameterized by some parameter theta. And now we can ask ourselves, how do we estimate the mean of the distribution? Let's say you only have 10 or 20 samples that you draw from a distribution. You could estimate the mean by, say, taking the first of the 20 numbers and saying, oh, this is my estimator for the mean. But that's going to be a pretty poor estimator. So what you really want to do is average the numbers that you have and say, okay, this is my estimator for the mean. For the median of a distribution, you're going to take the median of the sample that you've got and say, okay, this is my estimator for the median. For the variance of the distribution, again, a possible estimator is, you take, you actually compute the mean first, you subtract the mean from all the numbers, and you average the square loss, the square of that. So basically, when you've got a quantity that you want to estimate, you can do a better or a worse job. And we're going to introduce a risk function that tells you how well you're doing at estimating something. So the performance of an estimator is evaluated by computing its risk, and that is the expected value of a loss function. So in what I wrote there, the risk, let's say you've got theta hat, which is an estimator for quantity theta. Theta hat will clearly depend on the samples that you have so far. And the risk is the expected value of a loss. So your loss could be the mean squared error loss. So let me write down a few loss functions. So you can have a very frequently used loss is this squared error loss. Another one is hinge loss, which looks like kind of like this. So let's say this is your error, and this is your loss. So at first, when you make no mistake less than say epsilon, your error will be 0. Okay. After your error gets larger than that epsilon, it will increase like this. It will increase linearly. So this is called the hinge loss, and you'll make friends with this because you'll use it in SVMs for support vector machines. So support vector machines explicitly minimize this hinge loss. And of course you have 0-1 loss, which is I expressed it in data. So let's see. So this is okay. Would this be a good idea for if you're trying to do regression? So regression is when you estimate a real valued function based on the sample size. And my question is, would using this 0-1 loss be a good idea when doing regression? Oh, so did you guys understand what regression is? Okay. Okay, so do you think, is this a good idea? Okay, who thinks it's a brilliant idea?
But
Sorry?
the answer you're looking for is no.
Yeah, okay, but do you guys understand why it would be a terrible idea to estimate this?
Well, because when you're doing regression, you have real value things, which means that you have like a whole range of values, not just right and wrong.
Exactly. Right. Yeah, so it would be a pretty poor way to train a regressor. This, on the other hand, is used, and it's a good. Okay. So, okay. So the risk is just the expected value of that loss over the entire parameter space. So the expectation in the risk is taken over the parameter space. So we've got expectation over theta. So you're going to integrate over theta. Okay. All right. Now, let's say we're trying to do, as I said, regression. So y is a function of x plus some noise epsilon. So we're going to compute the error as the expected value of f of x minus f hat of x squared. Okay, so I think there's a parenthesis missing there, so we want to square the error there. Okay, this actually decomposes into two quantities. The bias of f hat, which is how different is it from what we're trying to estimate, and the variance of it. So let's say we were trying to estimate the mean of a distribution, and we always said, okay, the mean is 0. Independent of what samples we observe, the mean is 0. Well, if we did that, the variance of our estimator would be 0 because it never changes. On the other hand, its bias would be huge. Specifically, it would be mu squared, where mu is the thing we're trying to estimate. Okay, when I say bias, so it's without that square thing. It's actually the absolute value of the difference. Okay. Okay, questions so far? So we're done with estimators of risk for now. Okay. So let's review conditionals. So a conditional variable is something that is defined like that. So the probability of x given y is the probability of the joint over p of y. So x given y is a different random. Think of that as a different random variable. Now, conditional independence means that the joint variable x, y given z, the probability distribution of that variable can be written as a product of x given z and y given z. So x given z and y given z are two independent variables. Now, I enumerated some properties of conditional independence. So you're going to have some other properties of conditional independence to prove in your homework. So if you have trouble understanding of any of these, let me know, and I might send you proofs of these via email or something. So I don't think there's time to actually derive the proofs right. But these are some properties which you might find useful in doing some of your homework. Okay. And you'll get these slides, so you don't need to write them down. Like I'll send the slides. Okay. Right. Now let's recap base rule and probabilistic inference. So we've so far introduced the likelihood function, which is basically the probability distribution given some parameters. So P of some sample data which we have given theta is the likelihood of the data given the parameter of the distribution. The maximum likelihood estimator can be obtained by doing the argmax over that probability distribution when our data is given. Now, the question is, what if not all values of the parameter are equally likely? So theta itself is distributed according to some prior p theta. Then we can apply the base rule and get the posterior, the probability of the parameter given the data. So how likely is a certain value of the parameter given the data that we have seen so far? Okay. And because p of data doesn't really depend on our parameter, instead of maximizing the entire fraction, we can just maximize the top part. So it'll be the product of the likelihood and the prior. So that by maximizing that, we'll get the maximum a posteriori estimator. When are the map and the MLE equal? So for which kind of prior are the two estimators the same?
Uniform.
Yeah, exactly. It's a uniform prior. Everyone get why you need a uniform prior? Okay. All right. Well, who doesn't understand why you need a uniform prior? Okay, so you need a uniform prior because you're gonna have a set of p of theta. Here, you're going to have a constant, right? And you can.
Is uniform distribution the only kind of probability that makes this constant?
Yeah, pretty much. Well, because otherwise, except wait, you could have a the simple answer is yes. The more complicated answer is you can have a probability distribution which measures 0 in certain values of your theta. And for that one, this will also happen. But that's a very, that's kind of a big, yeah.
The first part of the last line makes it seem like that is equivalent to the maximum with an estimator.
Okay, oh, sorry, yeah, you're right. You know, there's a typo. It should be P of theta given data. Okay, thanks a lot for pointing that out. I'll make sure to fix that before I upload the slides. Okay, thanks.
Should it be like?
Yeah.
I think it's should it be really?
So it should be, so the MLE is the estimator of P of data given theta. And the map is the estimate, the argument that maximizes P of theta given theta.
So it's not.
So there is a typo. Yeah, so it should be here instead of P of data
Oh, yeah,
given
there
theta,
we
it
go.
should be this thing. Okay. Yeah, thanks for pointing that out. I'll fix the slides. So I'm going to now define conjugate priors. So let's say the posterior distribution P of data given data is in the same family as the prior probability distribution P theta. Then these prior and posterior are called conjugate distributions, and P of theta is called the conjugate prior. So you're going to have like a task concerning conjugate priors in your homework. So what happens is sometimes when I put, like let's say I put I have a likelihood that's a binomial, and here I'm going to put a beta prior. What results is a beta posterior. Okay. Okay. So conjugacy is useful because it makes stuff easier to compute, and you're going to have such an example. And here's a list of likelihood functions and their corresponding conjugate priors. So as I said, binomial is its conjugate priors beta, Poisson gamma, normal, and the multinomial is a Dirichlet. So the I'll send you the derivation for the last one of multinomial likelihood and the Dirichlet prior to see kind of how that goes. Okay. Now the question is, given some parameters of the likelihood and some parameters of the conjugate prior, the question is, how do we compute the parameters of the posterior? And the answer is you basically apply this formula. So actually you compute this product, and then you normalize because you know that P of the posterior has to be a probability distribution. So it has to sum to 1. But you're going to see that in the example that I'll send. All right, so I'm going to give you like a probabilistic inference problem. This is kind of a preview of stuff that will happen later in the semester when you learn about Bayesian networks. So let's read the problem. So we're planning on a weekend biking trip with your best friend Min. So your path to outdoor leisure is strewn with many hurdles. Now, if it rains, your chances of biking reduce to half without counting any other factors. Independent of this, Min might be able to bring a tent, the lack of which will only matter if you notice the symptoms of the flu before the trip. Namely, if he can't bring a tent and you've got a flu, you're not going. Okay. Finally, the trip won't happen if your advisor is unhappy with your weekly progress report. Okay. We've all had problems like that. So let's see how we're going to model this this problem. How we're going to look at this universe in terms of random variables. So let's call the variable O the outcome, which symbolizes the event that the outdoor trip happens. A, the advisor is happy. R, it rains that day. T, you have a tent. And F, you show flu symptoms. The way you're going to model that through a Bayes network is like that. So you're going to have your advisor, rain, and the joint of the tent and the flu symptoms influence your life, basically. And they're going to influence your life in a way that is independent of each other. So let's count how many parameters determine this model. So there's one link between A and O. That is one parameter. It is A given O. Now, R given O is another parameter. And the conditional of f of t given O is a set of 3 parameters, because I'm going to have a table that has 4 elements, but which I know that it needs to sum to 1. So I'll have one constraint, which results in 3 free variables. Okay. So in this problem, we're going to give the values for each of these things. But otherwise, we would have had to estimate each of these. So we would have had 5 estimators to derive from sample data. Okay. So now let's see a realization of this. So let's say the weather forecast predicts a 20% chance of rain, and there's an 80% chance that your advisor will be happy with your progress, and you do not have the flu. So now the problem that I give to you is, what are the chances that the trip will happen? So you don't need to solve this. We're going to come back later when we actually do base nets. But just think of how you would do this given the structure that I just represented. So at first, we should consider whether the variables f and t actually influence the result, given that you don't have the flu. And hint number 2, the combinations of variables for A and R represent the partition. And you can use one of the formulas we used. So you're going to have probability of O to compute, and that you can write as a sum of conditionals summed over the sample space of A and R. Okay, so I think we're pretty much done with this. This was just like a teaser, so you don't have to actually do it. Just think about it. Okay. All right. Now, guys, do you have questions? Anything not clear in the lectures, or Okay. Yeah.
If there are things that are unclear to us, are there any books you recommend?
Things that are.
Books. Do you recommend?
Oh, books. So there's the Chris Bishop book. Also, there's Casella and Berger, that stats book, which if you took stats, you probably saw it. Also, Larry Wasserman's got a book, which is called All of Statistics. That's also useful for stats stuff. I guess there's the Hasty book, but yeah, that's pretty advanced. So far these are like start easy with the Bishop book. It depends on which type, part of the class you're having the trouble with. If you're having trouble with, okay, that's it. Okay, well, thank you guys for coming, and send me an email if you have one.
Do you need to stop this?
Sorry?
Do you need to stop this?
Yeah.